We have a great audience here. Thank you for being here. Not only are we live here in Amsterdam, but we are also recording this for people that aren't available to be here today. And that will be available to all of you in the Intertraffic app later on. So, hello there. Now, we have Lorenzo Meschini here from PTV Sistema, and he is going to tell us something about data-driven traffic management and how you can combine analytical tools with machine learning. Ladies and gentlemen, can I have a round of applause for Lorenzo? Lorenzo, are you okay?
Yes.
Yes?
Sure.
I have a microphone for later on for questions for the audience, so just so you know. Take it away.
So good morning or good afternoon to everybody. I'm Lorenzo Meschini. I'm Vice President for Product Management Engineering in Real-Time and IDS product at PTV. This is a presentation I prepared with my colleague Nora Sabo. And so what I'm going to talk about today is, of course, the title. You saw it and you hear the presentation. I'll try to give you a quick overview of what we did in the last 10, 15 years at PTV about traffic management. And that brought basically us where the title says. So just a few words about PTV. You see our vision: empowering transportation and mobility for clearer and smarter future. That means that we try to build software solution and we provide expertise to improve the design, the planning, the operation of transport system worldwide, being that moving goods or people around the world. It's a company founded in Germany 40 years ago, a bit more actually. Now it's a worldwide, with a worldwide presence, and I mean, you can see a few numbers up there. Now, where we started, what we wanted to do. Our topic was to, or what I'm gonna tell you today, among the many things that PTV does, is that we tried to build a new way to produce traffic forecast, traffic estimation in real time, few minutes, up to 1 hour ahead, to improve decision and operation, traffic operation, traffic decision support in real time. Now, the way we started that and the way we did that was with the idea to bring models or the modeling that is done for transport planning and traffic engineering into the traffic operation, combining together few ingredients: network models, so basically the representation of network, public transport, roads, together with the real-time data, so collecting continuously from the field information from detectors, from events, variable message signs, signals, current status of signals, and things like that, and to combine them into simulation, real-time analytical model that could continuously run simulation and update this forecast. To provide what? To provide a propagation, a space propagation, to have an estimation of what's going on where you don't have measure, where you don't have information. So to have a complete overview of what are the condition of traffic or mobility, queue, delay, number of people, number of vehicles moving in the different place of the network. To provide propagation in time, so to have the knowledge not of what's going on now, but what's going on in the future. As I said, 15 minutes, 30 minutes, 1 hour and a half, few hours tomorrow, and most important, to activate proactive decision making. So to be able in real time, in few minutes, to run an alternative scenario that will tell you what would happen if you activate some countermeasure in case what you expect is gonna happen in few minutes, you don't like it and you would like to improve it as a traffic or mobility operator. Now, could we do it in different way? That's a question that we kept asking ourselves in the last 15 years, I would say. So those are the three fundamental questions that we were asking ourselves. So what we want to achieve: traffic estimation, traffic forecast, and scenario decision support and scenario evaluation. Could we do it simply with data? using data. So just taking data to do that. Well, with data, you may know what's going on now where you have information. But you cannot predict the future just looking at data. Speed on a given road section now tells you nothing about what could happen at the speed in few minutes. And for sure, you cannot do decision support. You cannot run alternative scenario or to get the information about what could happen if you change something in the network or change something in demand. Statistical approach means really looking at historical data, time series, whatever, and trying to understand from the history, from the past, what could happen in the future. These, of course, are models as well, but they don't try to understand the phenomena. They just look at data and the correlation of data. Well, of course, you can have traffic estimation. You can forecast if basically what will happen is something that happened in the past significant amount of time. Otherwise, if you have an expected condition, something that really never happened, or if you want to do decision support, this kind of approach, it's difficult, that can help you. So in our view, what we were trying to do and what we did try to do, it worked. And actually, we had quite few projects with this approach. So in the last 12 years, we were actually creating a traffic control system, traffic management system based on this project around the world. I give you just a few examples. This one is one of the oldest we have. Is running is live since now 10 years, I would say. So it's traffic management system based on our technology, covering a region where we have about 5 million inhabitants, 34,000 kilometers of road network covered by our system, where we produce every 5 minutes a traffic forecast in terms of number of vehicles, speeds, queues, up to 1 hour, so forecast of plus 15, 30, 45, 60 minutes, and we update this forecast every 5 minutes. So within 5 minutes, we produce a new forecast. And okay, so the core, our system is used to cover these use cases, so to have a real-time traffic monitoring. By the way, we include into the we correct the simulation. We include into the simulation all the information coming from the field in terms of detectors, FCD data, speed data, events, cameras, variable message signs. All these information are included into our system to basically correct and the simulation in order to adapt to what's going on in the field at the moment in a completely automatic way. So those are the use cases we cover basically with this system. We are able to then support real-time traffic monitoring, so traffic estimation, sort of prediction, I said. Then based on that, there are generation of alarm in presence of that traffic disruption, which could be even forecasted, so not actually happening yet. The signal control system is also connected, and then this information also spread to the public, so through the website and app of the mobility agency of Regione Piemonte, this information is spread to the people. Now, this is also another project, other side of the world, I would say literally. City of Taichung is in Taiwan. And here, I think that the topic was to connect traffic estimation system with an adaptive traffic control, which is also a PTV product, called Balance. And there, we obtain what I call proactive adaptive network signal control. Why I call it proactive? Because when we do signal control with the detector, the system can optimize based on the measure, so based on what happened in the past, at the most few seconds before, but for sure not in the future. We use predictions of the model of the system to optimize traffic and to basically feed the signal control, the adaptive signal control, to obtain an optimization which is based on what could happen or what will happen. So that's actually better. And in fact, numbers showed us that we could get some significant improved in the traffic flow applying this approach. You can see it up there. Well, okay, that was good, but could we do better? Could we do better because world was changing? And when I keep this slide, because I have this slide since probably really 10 years. And these slides, it's quite interesting because it changed, because actually there are much more data available today. And machine learning, artificial intelligence techniques, which are not new, we know, are becoming again quite important because of the computing power and because of the big amount of availability of data which are available today, also in our field, in the traffic and transportation and mobility field. So, okay, that's the situation, but no, okay, just a moment, because that's a mistake, but can we do better than what we are doing today? So can we really, and our answer was yes, probably we should work a bit better on that statistical approach, which some 9 years ago we thought it was not good enough for what we want to do, but probably today, or actually a few years back from now, we could take it again into consideration. And then we did basically two things. One is what we call data-driven modeling. Data-driven modeling means, I mean, always we need data to build models. Mathematical models always built using data in our field, using mobility data, socioeconomical data, and so on. But the key element that we did here was to use floating car data, so trajectories from vehicles, from people, to, let's say, automatically build model, transport model that then we could put into our system, the system I was showing before. And in particular, what we are deriving automatically from this data are origin and destination trip, of course, by time of the day and day of the week. The distribution, even more important, so basically the observed path choices that are done by the vehicle, by the people in the different time of the day, and speed profile and pattern. All of these data allowed us basically to speed up the calibration of our models and to increase the quality of the model that we put in those traffic management systems. Then the other thing that we did was to go back to the idea that we could do better in terms of understanding of using machine learning and artificial intelligence in the field of prediction. We knew that, I mean, as I said, unexpected situations are difficult to handle with pure statistical approach. But what if we could do at least measure prediction? So to do a prediction on what it was measured on the field. Flows, speed, okay. Then that's what the idea we explored. We started to select and to have data coming from detectors, speed, flows. And with this data, we did what? We did some clustering, automatic clustering, unsupervised learning. So basically, we had a system that could learn pattern, of course, recurrent pattern. And quite interesting, this unsupervised in the sense that we didn't feed the system with data types or upfront information. We let the system recognize recurrent pattern in terms of, in this case, you see a flow profile, but we did the same with the speeds, and I will show you that in a few minutes. For example, I mean, I have just an example which is quite interesting. This is look like a Saturday. I mean, a human would call this pattern a Saturday, but this pattern was recognized only by the machine. And actually, in this pattern, there are some days which are not Saturday, but looking at the calendar were basically post or pre-holidays during Christmas time. So the machine was able to put together in, I would say logically, normal Saturday with some unusual Friday or different days of the week, because actually the traffic pattern was like a Saturday due to the holiday season. And that's just an example. And we use then this kind of clustering, again, automatically in real time, to make prediction in a fairly, I mean, the basic of this prediction, I can tell you, it's basically to say, okay, I have the pattern of today. I recognize what is the most similar pattern in my set of cluster. Well, not me, the machine does that. And then with some additional correction, it uses that pattern to predict what will going on that detector, on that particular measure. We have a project. We did a validation of this approach. We did a validation of this approach only using measures. So without coupling that with the model base, we want to see how good was the solution by itself. And the solution was applied for this German mobility data space, where we basically, in a productive environment, are producing forecast over 3,000 detectors on a motorway. Actually, let me run the movie while I talk. So you have here the dashboard. We have more or less 3,000 detectors providing in real time flow and speed information. So vehicle counts and vehicle speeds. And on top of that, we have this machine learning system producing a forecast on each detector of flow and speed updated every 5 minutes, up to 1 hour ahead. And the system is completely automatic, completely unsupervised. It's self-learning in the sense that periodically, automatically, the cluster I was talking before are updated based on the historical data that came into the system in the last 6 months or something like that. So this is a completely different approach from the model-based. This is an approach which is completely unsupervised and self-learning, so quite efficient. Of course, the limitation of this approach are that you get a prediction only where you have data, on the kind of data you have. If you have speed, you forecast speed. If you have flows, you forecast flows. If you have nothing, you forecast nothing. But please look at this is the historical data. You see the vertical now line is the now. What you see on the right of the vertical line is the forecast. On the left, you see the flows of the day. And on the right, you see the speed on the day. So you see really the capability of the machine to forecast also the drop of speed and the recovery of the speed after the bottleneck. However, why having forecast, statistical forecast or model-based forecast? Our initial idea and our idea is to combine them. And the way we combine, because we don't see it as an opposition, as two alternative approach. We think that actually they work very well in different cases. And the way we do it is to have forecast on the measures where we have the measures, and then we use the model, the model-based approach, the analytical approach, let's call it traditional, to propagate the forecasted measures on the network, or accordingly with alternative scenario, which can be run for decision support. So really, we combine the power of the model-based forecast with the machine learning forecast, and that creates an improved quality of what we can do. So if the question before was, can we do better? Yes, we can do better. And you see there on a particular network, this is the headquarter town in Germany, we were running a prediction only model-based and combining model-based and statistical forecast, and you can see the improved quality on a 1 hour forecast. So that's a 60-minute forecast. And if you ask me how we measure the quality, it's quite easy. Unfortunately for us, it's quite easy to measure the forecast because we do shorter forecasts. So we have the forecast of 1 hour, and in 1 hour we get the true data. So it's just, it's unfortunately quite easy to measure the quality of our system. I would like to be a transport planner doing 10 years, 20 years strategic plan with his model. So just to, close the message with in my way, I would say. Well, data are like raw elements with which you can do food. Maybe you can eat a tomato, but eating wheat is not really the best. So with raw data, there's not a lot you can do. However, you can use data to build maybe some tomato sauce or some pasta with data-driven model or machine learning approach. So transforming data into information, it's what we need to do, okay? But then, I mean, come on, why to choose? Why do we have to choose? Why we have to have model-based approach and machine learning, statistical-based or data-driven approach being opposite one to the other? Actually, for me, the best is to put a bit of olive oil on top of it and have a nice spaghetti al sugo, pasta asciutta, whatever you want to call it, okay? And that's how we see it. Put all together in a smart way, in a nice way. Please don't just throw the tomato sauce on the pasta. That would be a mess. You need to do a nice sauce. But then, in this way, you really get the best out of it. And that's it. So that's, well, maybe 1, 2, 3 things, actually. So I said the first two. Data-driven model methodology allow us to go faster in building the models. So really, thanks to the data available, we can be faster and have a better quality. We want to combine different approaches together to reach the result we want to do, which is a reliable traffic forecast for decision support in traffic management. There is a last warning. In our field, still today, and maybe I will change this slide in a few years, but still today, to have big data which are clean, normalized, and most importantly, labeled to train artificial intelligence machine learning system is not so easy. To find this data available in big sites and so on. So that's why today is still not so easy to apply this kind of approaches. But I'm sure I will be wrong sooner than I would expect. But today is still a problem. And I mean, that's it. So thank you for your attention and attending. And maybe
Thank you, Lorenzo. Thank you. Do we have any questions from the audience? You have a big audience. I need to help me if someone's raising their hand because it's difficult to see through the lights. Yes, I see you. Could you introduce yourself as well, please?
Yes, my name is Ricardo Butraki. I manage highways in the US. And my question is, why do you say that data availability is a challenge when most cities or operators have a wide range of data available for them?
Thank you.
Yeah, thank you for the question. The label data. I mean, and I was talking about the availability of data which can be used to effectively train machine learning or artificial intelligence algorithm in our field. Because in that cases, you need the data that contains the, let's say, the question and the answer, the input and the output. And that's not so easy in our field. I can make you a practical example of that, just to let you understand what I'm talking about. If you think about a typical problem that we have with trajectory data, understanding the mode of transport. So what kind of transport mode that trajectory was, or that person in that trajectory was using? Was a car, a truck, a bicycle, a moped, a public transport, and which kind of public transport walking? That's a crucial question for a system. Well, yeah, there are data available, but when you start digging into the data set and when you really ask yourself if there are data sets that will allow us to build products and not single project, because we build products at BTV, then you discover that's not so easy. I mean, clearly there are companies that has those data a lot, but they're not so easily available or obtainable, even paying. So that was the point.
Thank you. Thank you. Anyone else? Yes. Can you introduce yourself as well?
Yeah, hi. My name is Ilan Weizman. I'm from Axelion, Israeli software company. Actually, I have two questions about the predictive model. Do you use kind of trajectory data like a V2X or any other connected vehicle data? And if you can elaborate a little bit about the prediction model, is it a mesoscopic simulation or is it just machine learning model? Or
yes. So about the first question, we can use trajectory data to feed the model both historically, and I explained in that data-driven part, basically for the path, the basic path, to reconstruct the basic path choices of the people. In real time, we use it to get mainly real-time speed, so observed speed. And that part is used, so observed speed is used in real time to correct the model and then propagate this correction on the propagation mechanism. And regarding the model, it's a macroscopic model, dynamic traffic assignment. So it's an analytical model. It is dynamic, so it represents the variation within the day of the things. It's not stationary, so you can see queues, spillback, and things like that. But it's not microscopic, so it doesn't go down to the single vehicle for speed reason. So in this way, we can calculate a network, like a regional network, 100,000 links in 30 seconds.
Thanks. Anyone else? Lorenzo, I think that's it.
Okay, thank you very much.
Can you give me a hand? And yeah, can you help me?
Oh, yeah, sorry.
Thank you. Thank
Sorry.
you.
I understood.
Thank
you
you.
needed
Yeah,
to click,
yeah,
of course.
Yeah. This is it for you.
Okay.
Can I have another round of applause, please, for Lorenzo?
Okay, thank you.
You.
You want this?
Yes. Yeah. This is thanks. Our next presentation is about it's speaking about big data and how you could use Google and how you couldn't use Google data. So if you're interested, please stay put. We'll be back in slightly less than 20 minutes. So, and if not, please enjoy the rest of the RAI here at the Intertraffic 2022. See you later.